the scientists' understanding of the climate system and answering the key questions that can help resolve the uncertainty. The scientists' understanding of the climate system and answering the key questions that can help
still need measurements.
Resolve the uncertainty. The scientists' understanding of the climate system and answering the key questions that can
still need measurements.
resolve the uncertainty. The scientists' understanding of the climate system and answering the key questions that can still need measurements. Resolve the uncertainty. The scientists' understanding of the climate system and answering the
Some of those new processes still need measurements.
The future of science and the key to continue understanding and improving the lives of all of us who call this planet home. They are the future of science and the key to continue understanding.
The students do not normally have an opportunity to see this.
To show them that there's actually stuff beyond just looking at what's in a book is very invaluable.
It gives them meaning and relevance to the work that they do in school.
I can't stress it enough just how important it is for the students to make that connection, because that's where they make their decision as to what they're going to do for the rest of their life.
It's fantastic to have real scientists, real pilots, real engineers and technicians coming in and sharing their experiences with the kids, because that brings science to life.
So we are bringing our science into their classrooms, as well as bringing the students here to see our science in action. And we're hoping that this will inspire some of the students to pursue careers in science, technology, engineering, or math, and one day maybe even work for NASA.
I saw how excited the kids were, so it's awesome.
Record the GDC line. Motion power, go, Frank. Roger, power. S1C press complete, Frank. Roger, you're all good. 30 seconds. Recorder at flight speed. Minus 20 seconds. Minus 20. Nice release, are you ready? Ready, minus 10. Mark. 9. Starting mission. Flame burned. Engine arm. 5, 4, 3, 2, 1. All engines running. Launch commit. Okay, right on it. That launch start, right? Hold on.
So on December 24th, 1968, astronaut William Anders took a picture of the Earth. He was in Apollo 8 and he was orbiting the moon, and he took a picture of the Earth, what's called the Earthrise picture.
Oh my God, look at that picture over there. There's the Earth coming up. Wow, that's pretty. Oh, I got it right. Oh, that's a beautiful shot.
And you look at that and the vastness of space with this gray moon, and you realize what a unique thing the Earth really is. And the Earth doesn't come with an owner's manual. It's for us to try to figure out all of the complexity that we see here.
Our campaign is coming to an end, but new ones will continue exploring, making new discoveries. Our journey is not over. Keep watching. This is just the end of a new beginning.
My name is Sara Morales Serrano. I'm system engineer for Clean Space, and today I'm going to try to explain you what is the problem of the space debris and what do we do at ESA to solve it. So space debris is any man-made object that is in space and that is no longer functional. As you know, we have been sending spacecraft to space since the 60s when the space flight started, and not all of them have re-entered and have left the space free. So there are two main orbits that we occupy with these satellites that are the low Earth orbit, what is considered one important region that is highly populated, and there we send our mission, for example, for Earth observation, where we can see how the Earth environment is evolving, or we can do, for example, weather prediction to know which is going to be the weather tomorrow. But also there is other orbit, like for example the geostationary orbit, that has some characteristics that are very particular, that they are all the time on top of our head. So they are very good for doing telecommunication, so for example to have our TV at home, or to use our mobiles. Nowadays we have 5,000 satellites, more than 5,000 satellites in space, and only 2,000 of them remains operative. We have lots of rocket bodies, so parts of our launcher that have remained in space, and some events have created even more debris. These events are, for example, collision between two spacecraft that have generated a big cloud of debris that is orbiting the Earth, or also some other events, like for example, self-explosions of our satellite. How do we take care of the environment here on Earth? So what we do is to try to assess all the environmental impacts of our missions during the whole life cycle of our mission. So since the beginning that we are developing our missions until the end of life. And we take into account all the phases like manufacturing, the launch of the spacecraft, and also the operations of our mission. So for this, we use a methodology that allows us to calculate what are the environmental impacts here on Earth. Like for example, in climate change, all our emissions that we have to soil and also to the water, and all the possible toxic materials that we use in our spacecraft. And the aim is to try to find alternatives that are greener and then they are polluting less to the environment. We also try to take into account the environmental impacts in the orbit. So for this, what we do is to try first to reduce the number of debris that we are creating and to remove the ones that are already there. So first of all, what we need to do is to leave free this space of the orbit, so remove the debris from this spot that was occupying during the lifetime. And we have requirement that states that we have to re-enter in the atmosphere in less than 25 years after the end of life. This is for the low Earth orbits, but also for the geostationary satellites, they have a similar requirement to go to a graveyard orbit. As we said, we want to stop creating debris, so one important requirement that we have to follow is to deplete or empty our source of energy that we have in our satellite. So for example, the batteries, to make sure that they are empty at the end of life, so they will not explode. This one is also a requirement, and also another one that is very important to follow, that is we don't want to have any risk when a satellite or debris is coming back to Earth, so we don't want that it falls in our roof and it causes any damage to us. So we have different requirements depending on the size of the satellite. If we are a big satellite, we will go to an uninhabited region in the Earth, or otherwise we try to maximize the disintegration during the atmosphere, so we design our satellite in a way that will disintegrate faster. And we still need to do some actions in order to prevent the creation of more debris. And there are studies that show that we have to remove at least 5 large objects per year in order to stabilize the situation. For this, we have been studying during the past year several tools that allow us to remove the debris that are in orbit, Like for example, the nets that are like a fishing mechanism, it works in the same way. So we will drop a net around our spacecraft of our debris. We will grab it. It will be enclosed inside this net, and then we pull it back to the Earth to burn up in the atmosphere during the day. Another tools that we have studied is an harpoon. We shoot this harpoon against the satellite, so then it will go through it will capture it, and then we do the same way. We will re-enter our spacecraft. Then other tools that are more sophisticated and can help us to do future servicing in orbit could be the robotic arm that will go closer to our target, it will grab it, and then once it grabs it, it will bring it also back to the Earth to burn up. These are several tools. There are many more that are under study. And now at ESA we have our first mission that it has been announced, that it will go to grab one of these part of the launcher that is in space. We will grab it and bring it back to Earth. So as you can see, there are many things that we need to do. We have to start now, and this is what we are trying at Clear Space. Thank you very much.
It's all about flames, fluids, and materials research aboard the International Space Station. Hi, I'm NASA astronaut Tracy Dyson. Welcome to Station Life.
Houston on 2 for velocity confirmation. Go ahead and lead steps 4, 5, and 4, 6. We're moving on to step 5.
You will go right now for
You
that
can copy. Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
Welcome back. This month on Station Life, we're going to look at how the unique environment on board the International Space Station enables physical science research. Our space station is a laboratory, unlike any on Earth. As we orbit in free fall around the planet, we have the opportunity to control gravity as a variable in our research. The pristine microgravity environment allows us to observe aspects of fundamental physics that aren't possible here on Earth. You see, gravity often masks or distorts subtle effects such as surface tension and diffusion. On ISS, these forces can be harnessed for a wide variety of physical science applications. So on today's program, we're going to look at how the lack of gravity affects the physical sciences of flames, fluids, and materials.
The International Space Station is the largest, most complex object ever assembled in space, and is clearly visible from Earth with nothing more than the naked eye. From end to end, the station is slightly longer than an American football field.
The biggest shock, I would say, the biggest impact that I had during my flight is the first time I looked out the window of the orbiter and saw the space station. It was huge. It was huge and shiny and beautiful. Looking at it and knowing that a man-made structure that big is actually up there.
The interior of this incredible structure is larger than a 5-bedroom house, with 2 baths, a gym, and a 360-degree bay window. The station's mass is almost 1 million pounds, and it contains about 32,000 cubic feet of living space. The space station functions as a microgravity and life sciences laboratory, a testbed for new technologies, and as a platform for both Earth and celestial observations. The complex is made up of multiple interconnected modules, grouped together at the center point of a 357-foot-long integrated truss structure. Power is generated through 4 giant solar arrays attached to the ends of the truss. The pressurized components include 3 laboratories: the U.S. Laboratory Module Destiny, the European Research Laboratory Columbus, and the Japanese Experiment Module Kibo. The Russian service module is the structural and functional center of the Russian segment of the station. It provides living quarters, communication systems, an exercise facility, and flight propulsion systems. Other Russian segments include the functional cargo block, 2 mini research modules, and a docking compartment. The Italian Space Agency provided a permanent multi-purpose module, which can host up to 16 additional racks containing equipment, experiments, and supplies. There are 3 modules called nodes that connect the elements of the station and provide berthing ports. The primary residential areas include the Russian service module and Node 3 Tranquility, which contains a bathroom for crew hygiene and exercise equipment, a treadmill, and a zero-G weightlifting device. The Quest airlock provides the capability for extravehicular activity, or EVAs. This is the module that provides the exit for spacewalking astronauts to go outside the station to work. The cupola is a small module designed for the observation of operations outside the space station. Similar to a bay window in a home on Earth, but with a 360-degree view, the cupola allows crew members to observe the approach of vehicles, as well as all robotic arm operations and spacewalks. The Canadian-built space station robotic arm is a larger version of the arm on the space shuttle, and is used to move equipment and hardware around outside the station. The space station is the home of 6 full-time crew members and is made up of astronauts and cosmonauts from nations around the world. More than 200 people have visited so far, and at least another 120 will live there over the next decade.
When you're up there for 6 months, or in Scott Kelly's case, an entire year, it's really the working in space part that becomes kind of the thing you love the most. It's the thing that gets you through the days. You're working with these professionals on the ground, and a lot of them have spent their entire lives working on these science experiments. And here we are up there, and we get to operate them. And it's really an honor to get to do that. And in many ways, those are some of my fondest memories of being in space. You get to work these experiments, and they're usually watching over your shoulder from the ground. And there was a lot of times where I would do something, whether it was fluids or with flame research, it really didn't matter. The investigator would just say, whoa, 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 wait, do that again. That was incredible and totally unexpected. And that was what just made you smile big up there when hey, we've been flying in space a long, long time, but we are still doing research that has unexpected results every single day on the space station. And I really love that about being up there.
In microgravity, something as simple as a candle flame looks and behaves completely different than here on Earth. Scientists are studying combustion on the space station with the hopes to improve efficiency of fuels and reduce pollution. Isn't that cool? Fire, it is often said, is mankind's oldest chemistry experiment. For thousands of years, people have been mixing the oxygen-rich air of the Earth with an almost endless variety of fuels to produce a hot, luminous flame. There's an arc of learning about combustion that stretches from the earliest campfires of primitive humans to the most advanced automobiles racing down the superhighways of the 21st century. Engineers studying burning to produce better internal combustion engines. Chemists peer into flames looking for exotic reactions. Chefs experiment with fire to cook better food. You would think there's not much more to learn. When it comes to fire, flames are hard to understand because they're complicated. In an ordinary candle flame, thousands of chemical reactions take place. Hydrocarbon molecules from the wick are vaporized and cracked apart by heat. They combine with oxygen to produce light, heat, carbon dioxide, and water. Some of the hydrocarbon fragments form ring-shaped molecules called polycyclic aromatic hydrocarbons, and eventually soot. Soot particles can themselves burn or simply drift away as smoke. The familiar teardrop shape of the flame is an effect caused by gravity. Hot air rises and draws fresh, cool air behind it. This is called buoyancy and is what makes the flame shoot up and flicker. But what happens when you light a candle, say on the International Space Station? In microgravity, flames burn differently. They form little spheres. Space station flame balls turn out to be wonderful mini labs for combustion research. Unlike flames on Earth, which expand greedily when they need more fuel, flame balls let the oxygen come to them. Oxygen and fuel combine in a narrow zone at the surface of the sphere, not here and there throughout the flame. It's a much simpler system. Recently, on a space station experiment called FLEX, where scientists learned how to put out fires in microgravity, they noticed small droplets of heptane were burning inside the FLEX combustion chamber. As planned, the flames went out, but unexpectedly, the droplets of fuel continued burning. The flames are there, just too faint to see. These are cool flames. Ordinarily, visible fires burn at a high temperature between 2200 and 3100 degrees Fahrenheit. Ordinarily, visible fires started out at temperature between 2200 and 3100 degrees Fahrenheit and began to go out. Ordinarily, visible fires started out at temperature between 2200 and 3100 degrees Fahrenheit and began to go out. Ordinarily, visible fires started out at temperature between 2200 and 3100 degrees Fahrenheit and began to go out. Produce carbon monoxide and formaldehyde. Similar cool flames have been produced on Earth, but they flicker out almost immediately. On the space station, however, cool flames can burn for nearly a minute. But there are practical implications of these results. For instance, they could lead to cooler auto ignitions. One of the ideas that auto companies have worked on for years is HCCI, short for homogeneous charge compression ignition. In the automobile cylinder, instead of a spark, there would be a gentler, less polluting combustion process throughout the entire chamber. The chemistry of HCCI involves cool flame chemistry. The extra control we get from the steady state burning on the space station will give us more accurate chemistry values for this type of research. The extra control we get from the steady state burning on the space station will give us more accurate chemistry values for this type of research.
Absolutely, yeah. And it's just like in the pool instead of that, with the exception of that big blue planet down there.
Exactly.
As the International Space Station flies 257 statute miles over the coast of Chile, Terry Virts in the initial moments of his first spacewalk. As the International Space Station flies 257 statute miles over the coast of Chile, Terry Virts in the initial moments of his first spacewalk.
To guide
As the International Space Station flies 257 statute miles over the coast of Chile, Terry Virts in the initial moments of his first spacewalk.
Sapphire is
Space Station flies 257 statute miles over the coast of Chile, Terry Virts in the initial moments of his first spacewalk. Space Station flies 257 statute miles over the coast of Chile, Terry Virts in the initial moments of his first spacewalk.
Once at the station, Sapphire will remain on shift until all the supplies are offloaded by the crew of astronauts.
Hi everyone, Kevin here. Today I want to show you how you can remove the background from the video, whether you're recording or streaming, so you can create something that looks like this. Whoa, check out me flying this plane. This is pretty sweet. Whoa! Barrel roll. If you are not familiar with this, this guy TV is really that was pretty awesome. So whether you're walking through a PowerPoint presentation, whether you're demonstrating something on your desktop, or maybe you're just having a little bit of fun and you want to appear in front of your team, whatever your reason, it's really easy to do, and I'll show you step by step how you can pull this off. You don't have to buy any fancy equipment. You don't need a
so you can just click on that. If you've never heard of OBS before, it's a free and open source video recorder and live streamer. It works extremely well. In fact, I use it for recording all of my videos on this channel. If you've never heard of OBS before and you're interested in just how to get started with it, I've included an intro video in the description. The great thing about OBS is whatever platform you happen to be on, whether it's Windows, Mac, or Linux, you can install OBS. Run through the installation process and then join the video again. Once you finish downloading OBS, head over to the website webex.com. We're going to use WebEx to capture our video and remove the background. WebEx is entirely free to sign up for and to use. Go here if you don't have an account yet and start for free and then sign in. Alternatively, you can also use Zoom or Microsoft Teams or video conferencing software that will capture your video start for free background. I simply happen to be choosing WebEx Meetings today because I think it does a very good job at removing the background. Once you create an account for WebEx Meetings, over on the left-hand side, click on Downloads, and then within Downloads, you can download the desktop app. The desktop app will allow you to remove the background from your video. We are making some fantastic progress. Next, we need to create a green screen. I know, I said you don't need a green screen, but this is going to be a virtual green screen that we could create on our computer. I have Paint opened up. This is an application that comes pre-installed with Windows. Simply go to your Start menu, type in Paint, and then launch this application. Within Paint, let's click on the green color, and then over at the Paint bucket or the Fill tool, let's click on this and fill in a green background.
Shall we?
All right, that's our green screen. The next thing that we need to do is click on File and save this. I'm going to simply put this on my desktop, and I'm going to call it Green Screen. Once I finish titling it, let's click on Save. You can see my green screen right here on my desktop. We're almost ready to get this working. Now that we have our virtual green screen, head over to your favorite video conferencing software. Once again, I'm using WebEx Meetings today, but you can also use Zoom or Microsoft Teams to pull this off. We're simply using the video conferencing software to remove our background. We're not actually going to meet with anyone else. This is going to be a solo meeting. On WebEx Meetings, I'm going to click on Start a Meeting. This opens up WebEx Meetings, and I can now see myself. Hi everyone, good to see you again. Now I want to use my virtual green screen, and I want to put that in back of myself so you no longer see this background. How do we do that? Well, up here in the top right-hand corner, I have the option to change my background. Let's click on that. I see all of the different virtual backgrounds. I could blur my background at different photos, but we want to use a virtual green screen. In the bottom right-hand corner, there's the option to add an additional background. Let's click on that. This opens up the Windows file picker. Navigate to where you saved your green screen. I put mine on the desktop, so I'm going to select it here and then click on Open. Look at that. I now have my own virtual green screen in back of me. So next, let's go into OBS. Next, head over to OBS, and the first thing that we need to do is add a new scene. To add a new scene, go to the bottom left-hand corner and click on the plus icon. You can name the scene whatever you want. I'm going to call it Green Screen. Once you finish typing in your name, click on OK. Now that we've added our new scene, we now need to add some sources. Right here, also in the bottom left-hand corner, let's go to Sources and click on the plus icon. Within this menu, let's click on Windows Capture, and we're going to capture the video from WebEx Meetings. Once again, you could also select Zoom or Microsoft Teams. This allows me to name the source. I'm going to call it WebEx Meetings Video. Once I finish typing in a name, I'm going to click on OK. This opens up a dialog where I can choose what window that I want to include. Within this drop-down, I can see all the different windows that I have open on my desktop. Navigate.
A normal coffee cup or a normal open container just simply won't work in a weightless environment because the liquid will be in the bottom of the cup and you tip it up and it still stays in the bottom of the cup. If you move it around too violently, it'll all splash out and make a big mess. So we end up having to drink our beverages through a straw from a bag. Makes you feel like you're a big insect sucking the juices from another insect. I wanted to see if I could figure out a way to have an open container cup in a weightless environment, which would allow you to drink your tea and your coffee in a manner that's commensurate with how people drink their beverages on Earth. Taking some of my surface chemistry that I learned in college, I devised a cup with a special shape. The cross-section looks kind of like an airplane wing, where it has a cusp, and the cusp will allow channel flow, so the liquid from the bottom of the cup will float up and just park itself right next to the rim, and then you can drink it. And it allows a crew to share a communal beverage. You could share tea. Maybe you just come in from doing a spacewalk or something and you want to celebrate a little bit. If you have a real cup, an open container, it's so ingrained in human beings, it's so ingrained in culture, it adds back the dimension of what it's like to be a human being in a civilized way.
Okay, flames and fluids are acting a little differently. But that's not all. Take a look at how microgravity affects colloids, magnetic fluids, and smart materials.
If you have a smartphone, take it out and run your fingers along the glass surface. It's cool to the touch, incredibly thin and strong, and almost impervious to scratching. You're now in contact with a smart material. Smart materials don't occur naturally. Instead, they're designed by engineers working at the molecular level to produce substances made to order for futuristic applications. The Corning Gorilla Glass that overlays the displays of many smartphones is a great example. It gets its toughness in part from fat potassium ions stuffed into the empty spaces between old-fashioned glass molecules. When the molten glass cools during manufacturing, dense to packed molecules solidify into a transparent armor that gives Gorilla Glass its extraordinary properties. Around the world, designers are working on other smart materials, such as alloys that can change shape on demand, plastics that heal themselves when ruptured, and fluids that obey magnetic commands to flow or stiffen under computer control. One of the greatest challenges in creating a smart material is arranging the molecules. They're so small. We want to create a new class of materials beyond smart. We need genius materials, materials that arrange themselves. The research to accomplish this is already underway on the International Space Station. Dr. First is the principal investigator of an experiment called In Space 3. In the microgravity of Earth orbit, vials of fluid mixed with very small colloidal particles, about 1/millionth of a meter in diameter, are exposed to magnetic fields. Magnetism can be switched on and off again very rapidly. This jostles the particles, causing them to bump together and self-assemble into microscopic structures. These structures can be very difficult to predict, even using cutting-edge models running on supercomputers. Astronauts enjoy watching this process in action through microscopes. Because the samples are backlit by a green lamp, they sometimes call it the green blob experiment. First recently won an award from the American Astronautical Society for his work on In Space 3. Just by toggling a magnetic field, we're learning how to take many kinds of microscopic building blocks and get them to spontaneously form interesting structures. Recently, observers have seen the colloidal particles forming long fibrous chains. First speculates that these could lead to materials that conduct heat or electricity in only one direction. The experiment has also yielded crystalline structures that the team is just beginning to investigate. The fluids underlying these tests are themselves very smart. They're called magnetoreological, or MR fluids, because they harden or change shape when they feel a magnetic field. If you own a sports or luxury car, you might have MR fluids in your shock absorbers. The stiffness of magnetic shocks can be electronically adjusted thousands of times per second, providing a remarkably smooth ride. Similar, but more powerful devices have been installed at Japan's National Museum of Emerging Science and China's Dongting Lake Bridge. They're there to counteract vibrations caused by earthquakes and gusts of wind. Some researchers have speculated that MR fluids might one day flow through the actuators and hydraulic dampers of robots, moving artificial joints and limbs in lifelike fashion. Scientists and researchers are using these fluids as a laboratory for studying self-assembly. MR fluids are, by definition, responsive to the magnetic nudging that sets self-assembly in motion. Furthermore, in space, the particles don't sediment out due to gravity. We can study the full 3D evolution of the material. Varying the shape of the colloidal particles, the cadence of magnetic toggling, the temperature of the fluid, and other factors will allow researchers and astronauts to further explore the frontiers of self-assembly. Touch the surface of your smartphone again. That's just the beginning.
As you can see, our International Space Station is an unprecedented research platform in space, allowing researchers and scientists to conduct experiments that can't be done anywhere else. This work off the Earth will lead to a better understanding of the fundamentals of combustion, surface tension, and colloids in the absence of gravity, benefiting us by helping us to make more efficient combustion engines, better portable medical diagnostics, stronger, lighter alloys, medicines with a longer shelf life, and buildings that are more resistant to earthquakes. Research on the International Space Station continues to improve life here on the Earth. Be sure to stay in touch and follow us on Facebook and Twitter for the latest research news, and don't forget to download our app on your mobile device. Until next time, we're working off the Earth for the Earth.
The safety discipline has a history of learning from the past and ensuring we don't forget those lessons. Sure, safety is built into our name, but every one of us at the Kennedy Space Center has the same responsibility. At NASA, our goals are daring and inherently risky. Sending humans to other planets means we're going to have to take some risks. We all need to ask ourselves, how do I balance risk and ensure mission success?
Okay, so on the mobile launcher here, we have dozens of high-pressure gas panels. They service the cryogenic systems, environmental life support systems, and other facility systems. And on these panels and between the panels, we have literally thousands of tube assemblies. Right now, we're going through our design certification process, and part of that process is to certify the pressure system. So when we do this pressure system certification, we work very closely with SNMA, particularly the Pressure Systems Manager's Office. Engineering prepares certification reports. We submit it to the Pressure Systems Manager's Office for review. They provide feedback to us and ultimately give us the final okay to certify the system. So while we were going through this process, we started submitting reports to the Pressure Systems Manager's Office, and they came back with some feedback for us about the vibration loads and the vibration analysis on tubing in the mobile launcher.
What we were seeing was these panels, even though they're shuttle heritage and they did survive shuttle launch loads, with the SLS rocket, we would have higher vibrational loads going into these panels. So we wanted to ensure that we wouldn't be exceeding the allowable stresses that are in our PVS codes and standards that we have to sign off the certification saying that these panels meet. So what we were thinking, the way to do this accurately would be to do a full finite element analysis. And since all these panels are unique, to pull that off would be an extensive amount of effort based on our analysis guys through engineering. It would take months, if not years, to do it all properly. And the overall benefit was probably low since we had confidence that these panels could survive a launch. We just didn't have the objective evidence to make that claim.
We worked really closely and we came up with basically about half a dozen different geometries and pretty accurately define all the tube assemblies we have in the mobile launcher. So our analysis group did analysis on some worst case scenarios using those different geometries to make sure that all of the supports that we already had installed and all of our tube routing was safe to operate and would survive the vibration loads during an SLS launch.
Right. This analysis was much more truncated than what it would have been required, but it did capture worst case scenario. The outcome of the analysis, we did have to add supports along some of the tubing runs because we found that they were unsupported, that stresses in certain areas would exceed allowables. But it was very minor compared to what the overall impact could have been to the schedule and cost to get us to where we're comfortable with using these panels with the SLS rocket causing the vibration on the ML.
Right, and this saved the engineering team a great deal of time. We were looking at an enormous analysis task that we were able to generalize and do on a much smaller scale. It was really helpful for us, and it also standardized the process that we use, and we were able to develop a standard now that we can use for future equipment too.
That's right.
Although we're pursuing our exploration goals as a team, it's critically important that we each take ownership of our own unique role. Competence and credibility are the keys to success. Know what matters. Look out for your teammates, serve your customers, and remember who the stakeholders are. Never lose sight of why we're balancing risk and safety. Safety and mission assurance, helping you manage risk to make the impossible possible.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach, pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
Hi, I'm Serena Anand-Chancellor. I'm a NASA astronaut, and this is Ask NASA, and I'm ready for your questions. All right, so first question, what is Artemis, or what is the Artemis program? So the Artemis program is our lunar exploration program. We will get to the South Pole of the moon by 2024, landing the first American woman and the next man. Why are we doing this? Well, in order for us to head towards Mars, we need a special place where we can practice, essentially develop robust engineering technologies, figure out how well the human does with long-duration spaceflight, learn how to build habitats, and we do all of this on the moon. Essentially, we practice. It's an engineering battleground, so we can go to Mars. What do you think it'll be like to go on an Artemis flight? Well, let me tell you, this would actually be really cool to go on an Artemis flight because we'd be heading to the moon. Now, what vehicle will we be traveling in? Well, it's actually the Orion vehicle right here. And some of you may recognize this. This is similar to the old Apollo capsules, but it is bigger, it is better. I've actually climbed inside the mock-ups, seen the systems, very modern systems. This is what will be taking us back to the moon. It's going to have the first American woman on the moon.
Serena, did you always want to be an astronaut?
I did, probably since I was 8 years old. My dad finally asked me one day, do you want to be an astronaut? And I said, yes.
What one personal item did you take to space?
Oh, I took multiple personal items. It wasn't just one. Funny enough, I took a back scratcher because you need a back scratcher wherever you go.
What food would you take to the moon?
Oh, easy. Cheeseburger, french fries, every time.
Yum. If you were in a dance-off with an alien, what song would you pick?
That's easy. It'd be Michael Jackson's Billie Jean. We played this song on the launch pad.
What do you miss the most about Earth when you're in space?
I missed feeling the Earth. So I miss the wind. I miss the rain. I miss the smell of the Earth, the smell of the grass. These are things you just can't imitate on station.
Is it scary being in space?
It's not scary being in space. I mean, it's your home, and it's the size of a 5-bedroom house. It's absolutely huge, and your friends are up there with you, so what's better than that?
Do you have a question for NASA? Send your questions to our experts on Twitter using hashtag AskNASA.
We are at Kennedy Space Center.
Every piece of hardware necessary to return to the moon is now here.
They are being assembled, stacked, fueled, and primed for flight.
Next time these engines fire up, we'll be on the launch pad to send an uncrewed Orion spacecraft around the moon on a flight test for the Artemis 1 mission.
It's been a journey of 1,000 miles from factory floors all across this country and around the world to here. And now the stage has been set.
We are seeing Artemis take her place.
The framework to support the enormity of this moment can't be measured in renovations and rehearsals alone.
But in the testing of a metal found much deeper.
With each segment built upon the one before it, the volume of anticipation can be seen rising.
For in addition to certifying what a host of testing has already previewed,
and liftoff. The dawn of Orion and a new era of American space exploration.
Artemis will demonstrate a new path to the moon for this generation.
Artemis 1.
An uncrewed test flight will be a final proving of every system
in every component
in the harshness of space.
A mission that, when successful, will open the door for the moonwalkers and lunar experiments
That so many have hoped and dreamed about.
We are going.
Three, two, 1, 0. Ignition. Liftoff.
Artemis 1 will lift off from Launch Pad 39B at NASA's Kennedy Space Center in Florida with 8.8 million pounds of thrust provided by the most powerful rocket in the world, our Space Launch System rocket, or SLS. The uncrewed flight will be the first integrated test of SLS, our new Orion spacecraft, and exploration ground systems at Kennedy. Artemis 1 will send Orion beyond the moon, 280,000 miles from Earth, farther than any human spacecraft has ever flown.
This is not NASA doing this. This is the United States of America doing this program, the Artemis program, and there are companies all across our country that have a part in it, so there is kind of this wave of excitement being generated just by saying, we're going back to the moon.
After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days to perform science experiments and technology demonstrations. Orion will make its multi-day outbound trips over several days to perform science. After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days to perform science. After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days. After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days. Orion will return home faster and hotter than any spacecraft has before. A primary goal of